Hello and welcome to this GeoStudio Tech Talk, part of our Sigma W Material Model series. Today's webinar will focus on a recent addition to Sigma W, the SANICLAY soil model. I'm Vincent Castonguay. I work as a research and development scientist with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 60 minutes long. Attendees can ask questions using the chat feature, and I'll make sure to respond to these questions via email as quickly as possible. A recording of the webinar will also be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields. Today's webinar relates specifically to Sigma W. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoStudio website. There you can also find videos, examples with detailed explanations, and engineering books for each of the products. Selecting an appropriate constitutive model is a key first step to successfully simulate the stress-strain behavior of soils. Constitutive models generally aim to capture specific aspects of soil behavior, so the selection process must be focused on the soil's most important behaviors. For loose sands, the most important behavior could be static liquefaction, for example, which would justify the use of Norsand. For today's webinar, our interest lies with the nonlinear stress-strain response of anisotropically consolidated soft soils, which warrants the use of the SANICLAY model. This is the soil model we will be exploring together in this webinar. The webinar will be divided into three parts. First, I will introduce SANICLAY's formulation and its most important features. Next, we will explore the soil model's input parameters. And finally, I will demonstrate how the model is used in Sigma W to simulate a series of anisotropic consolidated triaxial tests, and we will compare these simulation results with laboratory results. The goal of this webinar is to introduce GeoStudio users to a new soil model by providing guidance and background. To get the most complete and useful experience out of this webinar, I recommend you download the triaxial test on SANICLAY soil that is available on our website and review the concepts that we will be discussing today by yourself. Later in this webinar, triaxial compression test data from GANS 1983 will be used to compare SANICLAY's prediction performance against laboratory data. This dataset contains a large variety of laboratory tests performed on lower Cromer till, or LCT as we will call it, a low plasticity sandy silty clay. For the purpose of this webinar, we will draw our attention particularly toward the K0 consolidated drained and non-drained triaxial compression tests. These tests best highlight SANICLAY's abilities at simulating the behavior of anisotropic clayey soils. K0 consolidated triaxial tests are a subset of anisotropically consolidated triaxial tests and differ from usual CID or CIU triaxial tests in the way the initial consolidation phase is performed in the laboratory. As their name implies, CI tests are isotropically consolidated, meaning that the soil sample is subjected to the same confining stress on all its faces during consolidation. This creates an isotropic starting stress point before the start of the loading phase of the triaxial test. On a stress path plot, the consolidation path would be a straight line where the mean effective stress increases to 100 kPa in this example, but the deviatoric stress remains constant at 0 kPa. Since the same stresses are applied on all the faces of the sample, there is no deviatoric component to the stresses, or no shearing, if you will. On the other hand, K0 consolidated samples have their deformations monitored during the consolidation phase so that no radial deformations occur while the confining stress is increasing. So as the vertical stress increases during consolidation, the cell pressure is also increased independently to a value large enough so that no radial deformation occurs. This process is essentially recreating the stress path that occurs in an eudometer cell where the vertical stress is increased. In this case, the rigid walls of the eudometer cell will naturally prohibit radial deformations. As the vertical stress increases, the lateral stress also increases as a reaction to the sample being pushed against the cell wall. We call this process K-knot consolidation because the ratio of radial to vertical stress increments required to prevent radial strain is effectively the coefficient of earth pressure at rest, K-knot. On a stress path plot, K-knot consolidation is a straight line where both the mean effective stress and the deviatoric stress increase, following the ratio dictated by the soil's K-knot value. Another important topic of interest relating to consolidation is, of course, over-consolidation. Consider here the endpoint of our isotropic consolidation stress path as the new starting point for an unloading phase, so that over-consolidation is created. If we relax the vertical stress applied on the sample, the mean effective stress will decrease. The over-consolidation ratio, OCR, is then the ratio of the maximum and current mean effective stresses. In K-knot conditions, over-consolidation works the same way. Starting from the endpoint of our K-knot consolidation from earlier, if we relax the vertical effective stress applied, the mean effective stress will decrease. But interestingly, the stress path will not retrace the loading path. This behavior is mainly caused by nonlinear elasticity during unloading and by the development of over-consolidation. You are probably already familiar with Yackey's equation, which is often used to estimate K-knot for normally consolidated cohesive soils. But when that very same soil becomes over-consolidated, K-knot can in turn be estimated from the over-consolidation ratio and K-knot NC. An equation developed by Meyerhoff is often used to estimate K-knot once over-consolidation sets in. This is what we see in the unloading portion of the K-knot consolidation plot we were looking at a moment ago. When the sample goes from A to B as we relax the vertical stress, the over-consolidation ratio exceeds 1, and in this specific case is at 2. This affects the K-knot value, making it increase from a value of around 0.5 in the normally consolidated state to around 0.7 once OCR reaches 2. This change in K-knot explains why the unloading stress path deviates from what was observed during loading. If we were to unload even more to increase OCR to larger values, we would see an even greater effect on K-knot. This is what the plot you are seeing shows. This plot actually represents the K-knot consolidation procedure used for the lower chromotil laboratory data we will be using to evaluate SANICLAY's performance. Different soil samples are consolidated to OCR values of 1, 2, 4, and 7, following the K-knot consolidation procedure we described earlier. Some samples are tested undrained, performing what we call Traxel CAU test. This acronym stands for Consolidated Anisotropically Undrained. We can see on the stress path plot how the starting point of each test reflects how much unloading was necessary to reach the correct OCR values. In the case of OCR equals 7, the yellow sample, the sample was unloaded so much so that it is in tension, in fact, as the test begins. Notice both axes here are normalized by the maximum vertical total stress reached during each test to ease representation. Also note that the deviatoric stress, Q, used for the y-axis is defined as the difference between the vertical and horizontal stress. The corresponding stress-strain behavior for these undrained tests is shown on the right. Similar to the undrained test we just saw, some anisotropically consolidated drained Traxel test, or CAD test, were performed on LCT for various OCRs. This is the volumetric behavior plot, where we see mostly contraction for all samples, and the corresponding stress-strain behavior for these drained tests is shown on the right. As I said earlier, we will use both these drained and undrained laboratory test results to judge how SANICLAY performs. Now that the anisotropic consolidated Traxel test has been reviewed briefly, we can formally begin our introduction to SANICLAY. SANICLAY is a constitutive model introduced by Defalias and collaborators in 2006. The model was later revised in 2013 by Defalias and Tayebat. Both SANICLAY versions are available in Sigma W. We will see in this webinar how each differs from the other. SANICLAY is built on the critical state soil mechanics framework. Those who are familiar with the modified ChemClay constitutive model will recognize many of its features. What SANICLAY brings to the table compared to modified ChemClay is the ability to model the effect of anisotropy on soil behavior. If we strip SANICLAY of its anisotropic components, we are left with modified ChemClay as its backbone. To familiarize yourself with SANICLAY, I recommend you take the time to read the chapter dedicated to it in the Static Stress-Strain Modeling with GeoStudio book, available on our website. Reading the model's original author's paper is also recommended to appreciate the finer details of the model. To best appreciate what SANICLAY is and how it works, let me first introduce the concept of a yield surface. Most constitutive models use a yield surface to delimit elastic from elastic-plastic behavior. This yield surface is generally an equation in terms of stresses, sigma, and state parameters k. The state parameters are internal variables that evolve as the soil deforms on the yield surface. Here is a yield surface visually represented in 2D on a stress plot. Keep in mind the yield surface is generally a 3D equation, since stresses will develop in every direction for complex loadings. Any stress point such as A, located inside the yield surface, will only produce elastic strains once loaded. A point located exactly on the yield surface, such as B, will produce elastic-plastic response when loaded. Finally, a point located outside the yield surface, such as C, is inadmissible since it supposes the stress point currently exists beyond the resistance available. If stresses evolve towards C during loading, then the yield surface will have to evolve to accommodate this stress state. This is a process we call hardening. Each soil model has its own internal rules to dictate how hardening should proceed. Those familiar with the modified ChemClay model might have recognized the yield surface shown on the previous slide. This is in fact the classical modified ChemClay ellipsoidal yield surface. Its equation is expressed in terms of deviatoric stress Q, mean effective stress P, isotropic preconsolidation stress P0, and critical state ratio M. You will see in a minute how it also forms the basis for the SANICLAY yield surface equation. An important question that pertains to any soil model yield surface is, how well does this fit real data? Here we have some yield surfaces of natural clays taken from Graham and collaborators and Tavenin and Leroy. These yield surfaces, or limit state curves as they are often called in the literature, were measured or deducted from laboratory testing in various conditions. Notice how the yield surfaces are somewhat inclined toward the right and take on an elongated shape. This is caused by the natural anisotropy present in the grain structure arrangement of these natural clays. These yield surfaces differ quite a bit from the modified ChemClay ellipsoidal yield surface. Modified ChemClay, being a soil model based on isotropy, its yield surface reflects that inherent isotropy and is incapable of showing the anisotropic features found in natural clays. This is where SANICLAY differs. By rotating and pinching modified chemiclay's ellipsoidal yield surface, SANICLAY's yield surface succeeds in taking on a shape that is reminiscent of natural clays. This is done through the addition of a few new parameters found in SANICLAY. Setting these parameters back to modified chemiclay equivalent, we would find again the classical modified chemiclay yield surface. SANICLAY is thus truly a specialized version of modified chemiclay designed to take this somewhat crude soil model and adapt it to better represent the anisotropic behavior of natural clays. The changes required to take the modified chemically yield surface and alter it so that the SANICLAY yield surface is achieved are rather simple. They involve two new parameters, n and beta. N is the slope toward the top of the yield surface, similar to m in modified chemically, and is a model input parameter, while beta, an internal parameter, is the slope toward the tip of the yield surface, where the pre-consolidation pressure lives. As you can see from comparing both equations on screen, if beta is set to 0, which would lay the yield surface flat on the horizontal axis, and if n is set equal to modified chemiclay's m, SANICLAY's yield surface equation becomes exactly equal to modified chemiclay's. This new yield surface definition is one of the most important features of SANICLAY that makes it distinct from modified chemiclay. Another such feature is the definition of the plastic potential function in the flow rule. The plastic potential function is used within a constitutive model to define how plastic strains will develop once the stress state lies on the yield surface. The scalar multiplier is an internal parameter that is uniquely defined for each plasticity model. We call this equation the flow rule. Out of simplicity, many constitutive models will have their plastic potential function be equal to their yield surface function. This is what we call associated flow. Modified chemiclay and North sand are examples of associated flow soil models. The associated flow simplification is convenient because it avoids creating new model parameters, further complexifying the soil model. However, associated flow often fails to capture some aspects of soil behavior. Hence, the motivation to include non-associated flow rules in certain soil models like SANICLAY. In these cases, a plastic potential function distinct from the yield surface function is defined. In the case of the 2006 version of SANICLAY, the plastic potential function is defined as shown here, where alpha and p alpha are internal parameters, and m is the critical state ratio, a model input parameter. You may notice that the equation format looks very familiar, and you are right. The plastic potential function takes the same ellipsoidal shape as the yield surface function. Alpha and beta, m and n, p naught and p alpha serve identical purposes in each function to define their respective inclined ellipse. At any given stress point, where elastic plastic behavior is expected, the yield function is calculated based on the value of n and the current value of p naught. Next, the plastic potential function is computed based on the value of m, but p alpha here is adjusted so that the yield surface and the plastic potential functions coincide on the stress point. Each of SANICLAY's internal variables will evolve as plastic strains accumulate during loading. We won't review the specifics of these equations for the sake of brevity, but the important aspect of this part of the model to understand is that there are two mechanisms working together as plastic strains accumulate. The first mechanism is called isotropic hardening. This mechanism is responsible for the change of size of the yield and plastic potential surfaces. As shown in this example, the blue yield surface expands towards the dashed yield surface as isotropic hardening occurs. This hardening is caused by a change in p naught the isotropic preconsolidation pressure. The other mechanism at work is rotational hardening. As the name implies, this mechanism is responsible for the rotation of the ellipsoidal yield and plastic potential surfaces. In this example, the blue yield surface rotates towards the dashed yield surface as rotational hardening occurs. Notice this mechanism also alters the aspect ratio of the ellipse, making the ratio of the minor to major axis larger. This hardening is caused by a change in beta. I have not illustrated it here, but the plastic potential surface will also be affected by rotational hardening as alpha changes. I mentioned at the beginning of the webinar that there are two SANICLAY models available in Sigma W. The major differences between both models are related to how the internal variables evolve within the model. In both cases, plastic strains are the main driver for hardening. Both models use the same isotropic hardening rule. Both models even share the same parameter C to specify the rate of evolution of anisotropy when rotational hardening occurs. However, the models differ in how the rotational hardening rules are specifically formulated. The 2006 version uses a simplified formulation of rotational hardening, which can unfortunately lead to non-uniqueness of the critical state. The 2013 version fixes this issue at the cost of 2 extra input parameters. On the topic of distinctions between SANICLAY 2006 and 2013, I have plotted here a figure we have seen before in this webinar where SANICLAY's yield and plastic potential surfaces are shown. Remember how beta indicates the inclination of the yield surface and alpha indicates the inclination of the plastic potential surface? I had not mentioned it earlier, but this is only true for the 2006 version of SANICLAY. SANICLAY 2013 is a touch simpler in that regard, as alpha and beta are made equal at all times, internally. This means the yield and plastic surfaces always share the same inclination in SANICLAY 2013. The model still remains non-associated, since N and M can take distinct values, which will make both surfaces also distinct from one another. Interestingly, making both values equal would make the model associated. This concludes the introduction to the fundamentals of the SANICLAY model. As we have seen, the model takes the foundation laid out by modified ChemClay and brings it to a new level through the addition of anisotropy and rotational hardening. We have already encountered most of the model's input parameters in the previous section, but let's still take a moment to review them all together for each of the two SANICLAY flavors available in Sigma W. The stiffness parameters for both SANICLAY versions are the same and reminiscent of their modified ChemClay origins. Lambda is the slope of the normally consolidated line in void ratio log normal of mean effective stress. Kappa is the slope of the over-consolidated line in that same diagram. Both of these values are easy to measure from one-dimensional consolidation tests or during K-naught consolidation for anisotropic triaxial test. Finally, nu is the Poisson ratio, which depicts the interrelation between horizontal or radial and vertical strains within the elastic domain. The rest of SANICLAY's input parameters relate to the strength the model can develop. In the interest of time, I will not go over how to calibrate each strength parameter. Please refer to the parameterizing of the SANICLAY model document available on our website for a thorough description of the topic. NC and ME are the critical state ratio in compression and extension, respectively. It is generally accepted in the literature that the critical state ratio is a function of the load angle, or the relative magnitudes of the principal stresses, if you will. Specifying MC and ME will bound the domain where the general critical state ratio M is calculated. Remember that this parameter is used in the plastic potential surface equation. To best highlight the differences between both SANICLAY flavors available in Sigma W, I will continue the description of the strength input parameters for SANICLAY 2006 first and come back to the 2013 version next. The next parameter on the list is N, which defines the yield surface shape, similar to how M is used for the plastic potential surface. In this case, N is assumed independent of the load angle in the 2006 version. The next two parameters, C and C and X, are related to anisotropy and are used in the rotational hardening formulation. C dictates how responsive the model is to the development of anisotropy, while X limits the maximum influence of anisotropy on the response. For SANICLAY 2013, a different approach is taken for N, the parameter defining the yield surface shape. In this case, different values for N can be used for compression, NC, and extension, NE. This leads to a formulation where N is dependent on the load angle value just as M. C, the anisotropy evolution rate, remains an input parameter in SANICLAY 2013, just like in 2006. But there are three new input parameters that are now added to replace how the rotational hardening is calculated inside the model. The parameters S, Z, and Xi are related to this aspect of the model. Once again, don't forget that you can find on our website an example called Parameterizing the SANICLAY model, where our engineering team lays out the specific procedure to be used to adjust SANICLAY's input parameters. This document is a must-read for anyone willing to use this model. For the last part of this webinar, I will be working directly in Sigma W to show how SANICLAY can be used to simulate drained and undrained anisotropy consolidated triaxial test and how the model compares to the laboratory data for LCT we had looked at earlier in this webinar. Here I am in GeoStudio. To simulate these triaxial tests, I will create a new file, give it a representative title, and create a 2D axisymmetric geometry. We use this type of geometry when simulating triaxial tests to take advantage of the symmetry that exists for a triaxial sample. The axisymmetric geometry I will be drawing will be rotated around the x equals 0 axis to produce the virtual triaxial sample. I input the coordinates for the 4 points of my geometry, and I take the time to adjust the scale so that we can see the geometry more clearly and draw the region using the 4 points. With my geometry now properly drawn, I create the first Sigma W load deformation analysis. This analysis will be used to initiate the mean stress in the domain to 1 kPa. Before we make any big mistakes, let's just go ahead and save this file. I will also add some axes around my geometry and make sure that we can properly see the problem that we are trying to solve. I'll go in Define Materials and create a very simple isotropic elastic material for this first part of the simulation, since the goal here is simply to create a starting stress state for the analysis. I give this elastic material a very high elastic modulus to limit deformations, and once the material is defined, I draw it onto the region. Next, I create a normal stress boundary condition to apply a pressure of 1 kPa at the top and the right side of my sample. Once this is done, I can draw the boundary conditions relating to this analysis. I will fix the X deformation on the left side of the sample and the Y deformation at the bottom of the sample. This allows me to apply the 1 kPa stress on the top and the right side of the sample and have the sample remain immobile. Once the boundary conditions are properly drawn, I make sure that the mesh is appropriate for the simulation I'm performing. In this case, we only need a single element. And I'm now ready to solve this analysis. Once completed, I should check that the resulting stresses correspond to what I was expecting. In this case, the horizontal X and vertical Y stresses should be equal to 1 kPa. Here I'm plotting the horizontal stress, and I can clone this plot for representing the vertical effective stress, and we can see that both are equal to 1 kPa. Now that the stresses are initialized in my domain, I can go ahead and create a new load deformation analysis to perform K-naught consolidation. Our goal is to reach a vertical effective stress of 100 kPa at the end of consolidation. To increase the accuracy of the analysis using SANICLAY, I will adjust the tolerable error for stress update to a final value and also perform the analysis in 250 steps. I will now create a drained SANICLAY material using the input parameters that are appropriate for the lower chromatil, as we want to compare our simulation results to these laboratory results. Notice here that I will specify an OCR of 1 and a K-naught value of 1. My goal is to simulate the K-naught consolidation procedure and let these parameters evolve as a response to the loading and unloading that occurs. I'll be using the 2006 version of SANICLAY here. Once the material is created, I apply it to the region to replace the prior isotropic elastic material. Next, I need to create the boundary conditions that will replicate the K-naught consolidation procedure. In this case, I want the vertical effective stress to increase linearly from 1 kPa to 100 kPa. To achieve this, I create a normal stress boundary condition, for which I will also create a custom function. The function will ensure that the stress goes from 1 kPa at the beginning of the loading phase to 100 kPa at the end of loading, following a linear path, as we can see here. Finally, I'll apply a fixed X boundary condition to the right side of the sample to mimic the absence of radial deformation, as we want to replicate K-naught consolidation here. And then I apply the newly created vertical loading boundary condition at the top of the sample. I can now solve the analysis. Once this is done, as usual, I should go ahead and make sure my results are as what I expected, given the boundary conditions that I created. I'll be looking at the vertical and horizontal stresses, and as we can see here, the vertical effective stress reached 100 kPa at the end of consolidation, and we can see that the horizontal stress reached 48 kPa as a reaction to this consolidation. I can also plot other results that would be interesting to me, like for example the volumetric strain. As we can see here, compression is occurring as expected. And finally, since the SANICLAY model is used for this part of the loading phase, I can plot internal parameters that are specific to SANICLAY. For example, here I'm plotting alpha, the gradient of the plastic potential surface. I can clone this and also plot beta, the gradient of the yield surface. And finally, I can plot P naught, the size of the yield surface. I can then go ahead and select all these parameters and copy the data points to use in Excel, for example, to interpret the results. The stress path followed is shown here in blue. The yield surface at the end of consolidation is plotted in dashed green. Notice how the yield surface is already quite inclined and narrow. This is a direct consequence of the increase in beta value during loading. Similarly, the plastic potential surface, in dashed yellow, is now also inclined as a response to alpha evolving during loading. The end result of that K0 consolidation stress path is the creation of anisotropy within SANICLAY through its yield and plastic potential surface shapes. Back to GeoStudio. If I wanted to perform a triaxial test from the stress point where the sample currently is, that would correspond to loading it for OCR equal 1. But for the sake of demonstration, let's instead unload the sample to achieve OCR equal 2. To do this, I will go back to define project and add a new sigma W load deformation analysis as a child of the previous analysis. Similar to how we loaded the sample to 100 kPa, I will now create a boundary condition to unload to 50 kPa. Again, to achieve this, I will need to create a custom normal stress boundary condition function. This time, we will be unloading from 100 kPa to 50 kPa. At the end of unloading, the vertical stress will be half the value of what it was at the beginning of unloading. This will correspond to an OCR of 2. Once the boundary condition is created, I assign it to the top of the sample. See how now the arrows indicating the direction of loading are pointing outward. This is because we are unloading the sample at this stage. The other boundary conditions remain the same, including the fixed X boundary condition on the right side of the sample to once again model K0. Once the analysis is finished solving, I can verify my results, and here we can clearly see the unloading phase. Both the horizontal and vertical stresses unloaded from the value that they were at the end of consolidation. Starting from the blue square at the end of K0 consolidation, the stress path followed by the K0 unloading phase we just modeled in GeoStudio follows the red line and stops on the red square. We are finally ready to perform the triaxial test, where we are to load the sample up to 10% of axial strain in both drained and undrained conditions. To do this, I will go back to define project and add another sigma W load deformation analysis as the child of the K0 unloading analysis. I will then define the boundary condition responsible for shearing the sample. This uses a Y displacement boundary condition with a custom function once again. This time, the displacement is set to reach minus 0.005 at the end of the loading phase, which corresponds to 10% of axial strain. I finally applied this boundary condition to the top of the sample and also remove the fixed X boundary condition on the right of the sample to now allow radial deformations during the triaxial test. This really corresponds to the boundary condition of a normal typical triaxial shearing test. I solved the analysis and we can take a look at the results. To better view the results, I can plot a stress path plot. There we go. And I can also clone this and change the x-axis so that we can see the stress strain response. Notice how the response is initially very stiff. This is expected because this is for OCR equal 2. To perform that same triaxial test, but this time in undrained conditions, I can take advantage of the clone feature in GeoStudio. By returning to the Define Project menu, I can easily add a clone of the drained triaxial test. The clone analysis will be identical to the previous analysis, helping me save time. I now only need to switch the material model to undrained. I can do this quickly by once again using the clone feature and making a copy of the drained SANICLAY model I was working with and just changing the response to undrained. I leave all the other parameters the same. Internal parameters such as alpha, beta, p-naught, and OCR will be passed on by the parent analysis once again. I apply the new model. And since the boundary conditions have already been defined in the analysis which served as a basis for the clone, I am ready to launch the analysis. Once this is solved, I can take a look at the results and make sure that they correspond to what I was expecting. Now that we have seen how to perform the drained and undrained anisotropically consolidated triaxial tests for samples with an OCR of 2, allow me to take advantage of the magic of editing to quickly run through that very same process for OCR equal 1, 4, and 7. What I'm doing here is cloning the same analysis tree, starting with the unloading phase, and extending unloading to reach 4 and 7, and then performing the drained and undrained triaxial tests from there. For OCR of 1, I simply omit the unloading phase and fire the triaxial test right after the K-naught consolidation phase. The end result can be seen here with 4 child branches spawning off the K-naught consolidation analysis. Each branch contains a K-naught unloading sequence except for OCR equal 1, along with a drained and an undrained triaxial test. I've plotted here all the K-naught unloading sequences together with the yield surface at the end of K-naught consolidation in dash green. Interestingly, we can see here that each K-naught unloading stress path eventually crossed the yield surface. What this means is SANICLAY will behave elastically from the blue square up until the yield surface is touched. Once this happens, SANICLAY will behave elastoplastically, which will trigger hardening of the yield surface. To illustrate this effect, I have plotted here the yield surface at the end of K0 unloading for OCR equals 7 in dash red. This newly shaped yield surface is possible because of the accumulation of plastic strains, which affects the beta value. When the triaxial test is started from OCR equals 7, the red yield surface will bound the elastic domain, not the green yield surface. Now that we have seen how to use SANICLAY in sigma W to perform anisotropy consolidated triaxial test, let's have a look at how the model performs compared to the laboratory data for lower Cromer till. These are the results for the volumetric behavior. The lines represent the SANICLAY results from sigma W, while the squares represent the laboratory values. OCRs of 1, 2, 4, and 7 are shown in blue, red, gray, and yellow respectively for both data sources. We see SANICLAY performs well in predicting the volumetric trends observed in the laboratory. All samples show contraction, except for OCR of 7 where light dilation is observed. The corresponding stress-strain curves are shown on the right. The match between SANICLAY and the laboratory results is extremely good here. Every dataset shows close agreement, which is remarkable given the wide range of densities involved. Remember, we didn't alter SANICLAY's input parameters once to achieve these results. We simply let the model's internal parameters evolve as K0 consolidation and K0 unloading occurred. Finally, let us now look at the comparison between SANICLAY and the laboratory results for the undrained tests. We once again see the 4 data series for OCRs of 1, 2, 4, and 7 here for the stress pass results. Both data sources show relatively good agreement. Let me highlight here where each test starts for clarity. Notice how the initial stress path for OCRs larger than 1 are completely vertical. This indicates an initial elastic response, which is expected given their overconsolidation. On the right, we see the corresponding stress-strain response. Again, the results are in relatively good agreement. Once again, this nicely showcases how well SANICLAY is performing for a variety of densities and test conditions. The K0 consolidation and unloading portions of these tests allows the model to truly show its strengths. This concludes our webinar on the SANICLAY model in sigma W. The first part of the presentation focused on introducing SANICLAY and how it is an evolution of the modified ChemClay model. We then reviewed the input parameters for both SANICLAY flavors offered in sigma W. Finally, we explored how this model is used in sigma W through a practical example where anisotropically consolidated drain and undrained triaxial tests were simulated. We saw how well SANICLAY performed when comparing the simulation results with the corresponding laboratory results for lower Cromer till. Don't forget that you can download a similar example from our website if you want to give this workflow a try by yourself. Finally, if you'd like some new features and capabilities added in sigma W, don't hesitate to make suggestions by submitting support requests. We now have reached the end of this webinar. A recording will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us, and have a great rest of your day. Goodbye.